Welcome to this comprehensive guide on KEDA, which stands for Kubernetes Event-Driven Autoscaling. KEDA is a powerful tool that extends the native autoscaling capabilities of Kubernetes, allowing your applications to scale intelligently based on real-world events rather than just resource metrics. In this video, we'll explore how KEDA works, its architecture, and practical use cases that can help you optimize your Kubernetes workloads. This is part of our Kubernetes serverless series, where we dive deep into tools that make cloud-native applications more efficient and cost-effective. KEDA is a Kubernetes-based event-driven autoscaler that extends the native autoscaling capabilities of Kubernetes. At its core, KEDA allows you to scale your workloads based on external event sources, such as message queues, databases, or custom metrics. Unlike traditional autoscaling that relies solely on CPU and memory usage, KEDA responds to real events happening in your infrastructure. KEDA works alongside the horizontal pod autoscaler, which means it doesn't replace existing Kubernetes functionality, but enhances it. It's also an open-source project that has graduated from the Cloud Native Computing Foundation, indicating its maturity and widespread adoption in production environments. To understand why KEDA is valuable, let's compare it with the standard horizontal pod autoscaler, or HPA. The HPA has some limitations. It only supports CPU and memory metrics out of the box, it cannot scale deployments down to 0 pods, and it lacks native integration with external event sources. KEDA addresses all these limitations. It supports over 80 different event sources, including message queues like RabbitMQ and Kafka, cloud services like AWS SQS, and monitoring systems like Prometheus. KEDA can scale your workloads all the way down to 0 pods when there's no activity, which significantly reduces infrastructure costs. It also provides seamless custom metrics integration, making it ideal for event-driven architectures. KEDA's architecture consists of 4 main components that work together to enable event-driven autoscaling. First, the scaler connects to external event sources and retrieves metrics from them. Second, the metrics adapter takes those metrics and exposes them to Kubernetes HPA in a format it can understand for making scaling decisions. Third, the controller manages scaled object resources and activates deployments when events are detected. Finally, the scaled object is a custom resource that you define to specify the scaling behavior and triggers for your application. These components work together seamlessly, requiring minimal configuration while providing powerful event-driven scaling capabilities. KEDA supports a wide variety of scalers for different event sources. Some of the most popular include RabbitMQ for queue-length-based scaling, which monitors the number of messages waiting in a queue. Kafka is used for consumer lag monitoring, ensuring your processing keeps up with incoming data streams. Oz SQS provides cloud queue metrics for applications running on Amazon Web Services. Prometheus allows you to scale based on custom metrics queries, giving you complete flexibility. Cron enables time-based scaling for predictable workload patterns, and Redis tracks list length for applications using Redis as a message broker. Each scaler is designed to work with specific technologies, making KEDA incredibly versatile across different infrastructure setups. Installing KEDA in your Kubernetes cluster is straightforward and can be done using 2 primary methods. The first and most popular method is using Helm, the Kubernetes package manager. You start by adding the KEDA core Helm repository, then install KEDA into a dedicated namespace called Keda, which the command creates automatically. The second method uses YAML manifests directly from the KEDA GitHub releases page. You apply the manifest using kubectl with the server-side flag, specifying the version you want to install. Both methods will deploy all the necessary KEDA components into your cluster, and you can verify the installation by checking that the KEDA operator and metric server pods are running. The scaled object is a custom resource that defines how KEDA should scale your application. Let's break down its structure. You specify the API version as keda.sh/v1alpha1 and the kind as scaled object. In the metadata section, you give your scaled object a name. The spec section contains the important configuration. The scale target ref specifies which deployment or workload you want to scale. You set the minimum replica count, which can be 0 for complete scale-to-0 capability, and the maximum replica count to prevent unlimited scaling. Finally, the triggers section defines what events should trigger scaling. In this example, we're using a RabbitMQ trigger, but you can configure any of the supported scalers based on your infrastructure needs. One of KEDA's most powerful features is its ability to scale workloads down to 0 pods. Here's how it works. KEDA continuously monitors your configured event sources, even when no pods are running. When your workload is idle with no events to process, KEDA scales the deployment down to 0 pods, completely freeing up those resources. The moment new events arrive in your queue or stream, KEDA instantly activates the deployment, bringing it back up to handle the workload. The benefits of this capability are significant. It reduces infrastructure costs dramatically because you're not paying for idle resources. It optimizes resource utilization across your cluster, and it's perfect for event-driven workloads that have periods of inactivity followed by bursts of processing. Let's look at a concrete example of configuring a KEDA trigger for RabbitMQ. In the Triggers section, you specify the type as RabbitMQ. The metadata contains the connection details. The host parameter includes the full AMQP connection string with credentials and the RabbitMQ server address and port. The queue name specifies which RabbitMQ queue to monitor. The queue length defines the threshold. In this case, every 10 messages in the queue will trigger one additional pod to be scaled up. Finally, the authentication ref points to a Kubernetes secret that securely stores your RabbitMQ credentials, following security best practices. This configuration tells KEDA to monitor the specified queue and scale your application based on the number of pending messages. KEDA excels in several common use cases. For message processing, you can scale worker pods based on queue depth in systems like RabbitMQ, Kafka, or AWS SQS, ensuring messages are processed promptly without over-provisioning resources. Stream processing benefits from KEDA's ability to handle data streams with dynamic scaling based on consumer lag, keeping your processing pipeline efficient. Scheduled jobs can use cron triggers to run batch processing at specific times, scaling up for the job and back down when complete. Webhook handlers can scale API endpoints based on external metrics and events, responding to traffic patterns that traditional metrics might miss. These use cases demonstrate how KEDA bridges the gap between traditional resource-based autoscaling and real-world event-driven architectures, making your Kubernetes applications more efficient and cost-effective.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.